So, welcome to this session of the class. So, we will be basically now looking into the solution of cross flow filtration system. This will be valid for reverse osmosis, ultrafiltration as well as the microfiltration. We are looking into a two-dimensional mass transfer boundary layer analysis, and in the last class we have seen how the concentration profile in the mass transfer boundary layer will be solved, and then this concentration will be evaluated at y equal to 0 in order to get an idea of Cm, that is the membrane surface concentration, and how it varies with the hydrodynamic of the system. And then once we get that, then we will be hooking up with the transport loss through the porous membrane. Let us look into that. If you look into the solvent flux in the membrane, we get Vw is equal to Lp del p minus del pi, and we make it non-dimensional by defining Vw dE. We multiply both sides by d by d. So, it will be Lp d by d delta p minus delta pi. So, therefore, this will be nothing but non-dimensional permeate flux. Pw is equal to, let us say this parameter is b. This is so we write everything in the form of non-dimensional parameter. So, Pw is Vw d by d is non-dimensional, it is a Peclet number, it is basically non-dimensional permeate flux, and b is a non-dimensional parameter Lp d by d. So, this equation must be valid at every location of module or channel. Okay. So, this will be the equation that will be satisfied everywhere. Now, let us look into the other equations. So, if you remember that what is the equivalent diameter, we have defined earlier that equivalent diameter is nothing but 4 of half height for a thin rectangular channel. Now, if you remember that we have defined Vw as Vw Hx divided by u0 d square to the power 1 upon 3 is equal to A, and let us write it, take it on the other side, A u0 d square divided by Hx to the power 1 upon 3, make it non-dimensional. So, this becomes Pw is Vw d by d. So, A u0 d square d cube and Hx d cube to the power 1 upon 3, and we will just put H is equal to d by 4. So, this becomes 4 to the power 1 upon 3 A u0, this d will be cancelling out, d square divided by x d to the power 1 upon 3. So, now if you convert this into Reynolds and Smith number, this will turn out to be and then this will be raised to the power x to the power 1 upon 3 on the other side, x to the power minus 1 upon 3. Okay. So, now let us put in the non-dimensional form. So, Pw will be 4 to the power 1 upon 3 A u0 d square by x d, and make it and this. Okay. In this x is already included. So, we can take x out of this. So, it becomes, and if we make it make x non-dimensional, then this becomes, this x will be outside. So, x to the power minus 1 upon 3. So, 4 to the power 1 upon 3 A u0 d square by d times L, where L is the channel length. This becomes x to the power x star minus 1 upon 3. There will be a square. Now, what is this number? This is again a non-dimensional number. This is Reynolds Schmidt d by L. If you can open it up, u0 d by nu, nu is the mu by rho. So, this nu by d, this is d by L. So, this becomes u0 d square by d L. So, this becomes P w is now becomes 4 to the power 1 upon 3 A Reynolds Schmidt d by L to the power 1 upon 3 x to the power minus 1 upon 3. So, this will be the relationship how permeate flux is varying as a function of A as a function of x, and one can get an expression of A now as P w divided by 4 to the power 1 upon 3 Reynolds Schmidt d by L to the power 1 upon 3 x to the power 1 upon 3. So, now let us write down what are the different equations we are having. Different equations we are having is this will be expression of A, P w will be osmotic pressure model B times 1 minus delta pi by delta P, and you will be having the expression of I and Cm star will be 1 over 1 minus A r r I, and what is the expression of I? I is 0 to infinity exponential minus eta cube by 3 minus A eta d eta. Now, let us write down the different equations. Number 1, this will be then 2, this will be 3, and this will be 3, and this will be 4. Okay. So, let us write down the different. So, these 4 are equations. Now, let us see how we do the computation of the system performance and predict the system performance. Now, it will be a now next step is we will be doing an numerical calculation. So, at a particular x location, at a particular x star, we guess a value of Cm star, guess Cm star. Once Cm star is obtained, then is guessed, then from equation 1 evaluate P w from equation number 1. This is the osmotic pressure relationship. Once P w is known, then one can get the value of A, evaluate A using the P w at that particular x location from equation 5. So, what is our equation 5? In the previous slide, we write this is the equation 5. So, once we get the value of A, evaluate A from we will evaluate A from so 5 is not required, this is obtained from there only. So, we will be getting the value of A from equation 2. So, because we have obtained the value of P w from the osmotic pressure model, we insert that here. Reynolds Schmidt d by L are the operating conditions, d by L is geometric factor, 4 is a numerical value, x star we are evaluating at that particular x location. So, therefore, we will be evaluating A from equation number 2, and once we evaluate A, then we are in a position to evaluate the definite integral I from equation 3. So, once we evaluate the definite integral I from equation 3, then from we can evaluate, we can calculate Cm star from equation 4. So, let us look into the, let us go back to the equations. At a particular x location, we have guessed a value of Cm star. Once we guess the value of Cm star, we can evaluate P w, because delta pi will be function of Cm star only, all the other parameters are known to us. So, once P w is evaluated, we can get back to equation 2 and evaluate the value of A. Once we evaluate the value of C, we will be getting back to equation 3 and we will be evaluating the value of I, and this integration has to be evaluated numerically using a trapezoidal rule or a Simpson's rule. So, this infinity will be replaced by a higher value, let us say 5 or 10. So, let us say let us put it a value of 10 and evaluate the value of integral, then we will be putting another value of 15 or 20 and we will be evaluating the value of I numerically using trapezoidal or Simpson. If the answer of the two values will be different in the decimal places, let us say 1 or 2 decimal places, then we can take the infinity as the value of 10. Okay. So, once we evaluate the value of I, we have already evaluated the value of A, then we can calculate Cm star from equation 4 and then we will check whether this Cm star is coming close to the guess value or not. So, 6 is check absolute of Cm star calculated from step 5 minus Cm star guess is less than epsilon. This epsilon can be a small number. If it is not, then we have to guess the value of Cm. So, if not, then we have to guess another value of Cm and carry out this loop. If yes, then we have to again go to x star plus delta x star, the next x location, and redo these calculations iteratively. So, in the process what we will be getting? So, there will be two loops. One will be the inner loop where we will be calculating the Cm star from the algorithm at a particular x location, then we will be going to the next x location x plus delta x and redo the calculation iteratively. And likewise, ultimately what you will be getting? Ultimately, you will be getting Cm star as a function of x star. So, once you know the Cm star as a function of x star, then you will be getting the Pw as a function of x star and Cp star as a function of x star. So, we will be getting the profile of permeate flux, non-dimensional permeate flux as a function of x star and permeate concentration as a function of x star, and then this will be again we have to do a Simpson's rule and doing a length averaging. So, length average permeate flux will be nothing but 0 to 1 P w x star d x star and Cp length average permeate concentration will be 0 to 1 Cp x star d x star. So, therefore, one will be getting the length average permeate flux and permeate concentration and can get the system performance as a function of operating conditions. So, this way the osmotic pressure control can be predicted to a completely can be utilized completely predictive way. So, for a well defined system where we know the solute diffusivity, solute the geometry of the system perfectly, everything is known, then this osmotic pressure control filtration model can be utilized to get a system performance. Now, let us go a little bit ahead and let us look into the mass transfer coefficient, and then we will see how this mass transfer coefficient will be estimation of mass transfer coefficient will be helping us in reducing the rigor of calculation further. So, let us look into the length average permeate flux and evaluation of mass transfer coefficient. So, length average permeate flux will be given as we have described here 0 to 1 P w x star d x star. So, we have the expression of P w as a function of x star, we insert there that and see how much we are getting 4 to the power 1 upon 3 A Reynolds Smith d by L to the power 1 upon 3 0 to 1 x star to the power minus 1 upon 3 d x star, and ultimately we will be getting as P w bar is equal to 2.38 A Reynolds Smith d by L to the power 1 upon 3. So, we will be getting the expression of A as a function of length average permeate flux as A is equal to 0.42 Reynolds Smith d by L to the power 1 upon 3. So, we call this as lambda 0.42 lambda, where lambda is equal to P w bar divided by Reynolds Smith d by L to the power 1 upon 3. This lambda is also known as the suction parameter. It is a non-dimensional suction parameter. It indicates that the wall is really porous, and if the wall is impervious, P w equal to 0 and the suction parameter will be 0. Therefore, for an impervious conduit, when there is no wall porosity, P w that will be indicated by P w equal to 0. On the other hand, if we have a wall suction, there will be a definite value of P w bar, the length average permeate flux, and that will be there will be definite value of lambda not equal to 0. So, in case of no suction, there is no membrane is placed in the conduit, in the flow conduit, lambda will be equal to 0. In presence of membrane, lambda will be assuming a different a finite value. So, next we will be looking into the expression of mass transfer coefficient. So, if we go back to the expression of the indefinite integral 0 to infinity, the definite integral infinite integral 0 to infinity as exponential minus eta cube by 3 minus a eta. So, I am replacing a by 0.42 lambda eta d eta, and now we define the mass transfer coefficient as k Cm by C naught is equal to minus d del C del y at y equal to 0. That will be a typical definition of film mass transfer coefficient, and k becomes, so we make it non-dimensional, k Cm star minus 1 is equal to minus d. We replace del C del y in terms of non-dimensional in terms of similarity parameter eta. So, this becomes u 0 h x d to the power 1 upon 3 d c star d eta evaluated at eta equal to 0. Now, if you really do that, and we have already seen that Cm star is equal to nothing but the parameter k 2, and this d c star d eta at eta equal to 0 will be the integral constant k 1. So, mass transfer coefficient can be replaced as minus k 1 divided by k 2 minus 1 u 0 d square divided by h x to the power 1 upon 3, and k x k as a will be if you replace the value of k 1 and k 2, this becomes 1 over I u 0 d square h x divided raised to the power 1 upon 3. Now, we will be defining the Sherwood number in terms of k d by d, and this becomes the Sherwood number becomes 1 over I u 0 d square over h x to the power 1 upon 3, and if we now replace everything in the non-dimensional form, this becomes Sherwood as a function of x star is 4 to the power 1 upon 3 I Reynolds Smith d by L to the power 1 upon 3 x to the power minus 1 upon 3. So, this factor 4 comes from conversion of half height into the equivalent diameter, and L comes from non-dimensional version of x star is defined as x by L. So, we can get the length average Sherwood number. Length average Sherwood number will be nothing but 0 to 1 sh x star dx star, and this becomes 2.381 divided by I Reynolds Smith d by L to the power 1 upon 3. So, this is the expression of Sherwood number, length average Sherwood number in the case of membrane channel where the walls are really porous. Now, let us look into the various simplified cases. For case 1, P w equal to 0, then P w bar equal to 0, that means there is no suction and impervious conduit. Now, if we can really find out the expression of I, now this will become 0 to infinity exponential minus eta cube by 3 d eta, this becomes 1.29, and if we really put it there, then average Sherwood number becomes 1.85 Reynolds Smith d by L to the power 1 upon 3. Now, if you can recognize this equation, this is nothing but the Levex equation. So, for the that is coming from the heat and mass transfer analogy for the impervious conduit. So, we get back the Levex equation if we put wall suction is equal to 0 or the suction parameter lambda equal to 0 when there will be no permeate flux coming out of the system. So, next case 2, when wall suction is not equal to 0, P w bar is not equal to 0, then that means that you will be having a membrane channel and into the system. So, what we will be doing will be if you look into the value of lambda the is nothing but P w bar divided by Reynolds Smith d by L to the power 1 upon 3. For a typical value of lambda in membrane system, for microfiltration system P w bar will be quite high. So, in that case we will be having a high value of lambda. In case of reverse osmosis, P w bar will be quite less. So, we will be getting a less value of lambda, and typically this lambda varies from 0.5 to 10. Next, what we will be doing? We will be evaluating the integral I as a function of lambda numerically, and then we fit a curve of 1 over I as a function of lambda. If we really do that, then we will be getting Sherwood length average Sherwood is equal to 1.85 Reynolds Smith d by L to the power 1 upon 3 1 plus 0.32 lambda plus 0.02 lambda square minus 8 into 10 to the power minus 4 lambda cube. Now, this will be the expression of Sherwood number in a membrane channel when the walls are really porous. And now, this expression, if we put the no suction case, no suction means when lambda equal to 0, we will be getting back the Levex equation. So, this is the expression of Sherwood number by incorporating the value of suction parameter in the membrane wall. So, if you remember the Levex solution that was developed in 1885 and the modification of the porous wall, the Sherwood number will be has been developed recently in 1997, in late 90s. So, it will be what it indicates that the suction parameter increases the mass transfer coefficient of Sherwood number, and what is the extent of increase? The extent of increase will be given by this factor, and depending on the value of lambda, the porosity of the wall or permeability of the wall, the suction parameter will be enhanced the Sherwood number compared to the no impervious conduit or when the suction parameter will be equal to 0. Now, next we will be seeing how to utilize the Sherwood number relationship in order to find a quick calculation of the system performance quite easily. So, we will be looking into the faster procedure or algorithm. To calculate system performance using Sherwood number or average mass transfer coefficient. So, if you look into the boundary conditions at y equal to 0, at y is equal to 0, we had VW Cm minus Cp is equal to minus d del C del y, and at the same point we have the definition of mass transfer coefficient as k times Cm minus C0. So, if we consider the all average values, length average values, we will be having that VW bar Cm bar minus Cp bar is equal to KL bar Cm bar minus C naught, and in terms of non-dimensional parameter you will be getting Pw bar is equal to SHL bar RR 1 minus 1 over Cm star. So, Pw bar is equal to nothing but Vw bar d by d, and Sherwood is nothing but KL bar d by d. So, this relation will be giving you the expression of average value of wall suction parameter or the permeate flux with respect to length average permeate flux. So, you will be having the length average permeate flux, this expression Pw bar is equal to bar divided into RR 1 minus 1 by Cm star, and we have the osmotic pressure model Pw bar is equal to B times 1 minus delta pi by delta P. Now, we have the expression of SHL bar average Sherwood length average Sherwood number as a function of lambda, which will be nothing but Pw bar divided by Reynolds Smith d by L raised to the power 1 upon 3, and we have delta pi which will be function of Cm star. Now, we have two. So, essentially we will be having two equations and two unknown system. What are the unknowns? Pw bar and Cm star. So, now we have to solve two algebraic equations which are nonlinear and they are coupled. Again, this can be solved by using Newton-Raphson method iteratively. Therefore, now using the mass transfer, so what we have seen now in this class we have seen how to solve the detailed two dimensional model for osmotic pressure control filtration, and once you get the concentration profile, then if you hook it up with the transport phenomena through the porous membrane, then you will be getting a system performance. If you adopt to an algorithm which will be giving you ultimately the value of permeate flux and permeate concentration as a function of x. But if you remember, up to that point we have not used the definition of mass transfer coefficient. Next, what we have done, we have derived a fundamental relation of length average Sherwood number or mass transfer coefficient from the first principle and obtained an expression of Sherwood number. Now, using that definition of mass transfer coefficient, we have formulated the problem once again, but at this time it will be in the terms of all length averaged quantities. So, therefore, you will be getting ultimately landing up with two algebraic equations. Now, in this case we are not going to evaluate the profile of dependent parameter permeate flux and permeate concentration as a function of x location, and then doing one more length averaging by adopting Simpson's rule or trapezoidal rule. In this case, we have landed up into two algebraic equations directly having two unknowns, and one can get the length averaged permeate flux and permeate concentration directly from this equation using the Sherwood number relationship. So, that is why people used to find out the mass transfer coefficient in any transport problem, and then that will immensely simplify the solution of the problem in terms of the mass transfer coefficient. So, that will complete the predictive mode of how to predict the osmotic pressure filtration. And osmotic pressure filtration, if you remember, you will come across with the in case of the solutes which will be having a low molecular weight, for example salt. sugar, polyphenols, dyes, etc. where so we have seen how to in a cross flow system which will be quite frequently applicable for an industrial scale to model the system in an entirely predictive method. In the next class, what we will be doing, we will be looking into the importance of the batch cell and how to unstirred batch cell and how to model the unstirred batch cell quite accurately in a predictive manner using the similarity transform from the first principles. Thank you very much.